So in this video, we are going to see how to calculate the moment of inertia of a ring about two axes, about a first axis that passes through the center of the ring, and then about an axis that passes through the diameter of the ring. So if you haven't yet watched the introduction, because it's an introduction to this video series, I strongly recommend you to go and watch it first, because you're going to kind of have all the elements we need to jump into the subject. Okay. So the idea, of course, is always to calculate the moment of inertia of a tiny element of the distribution and then integrate over all the entire length or surface or volume, in the case you're having a surface or a volume distribution. In this case, we have a length distribution. So we have a ring that has a mass m and a radius capital R. It has a uniform length distribution. Okay, so the inner and the outer circumferences, they're actually it's very thin. Okay, the thickness is very small. It's just for you to not to confuse it with a disc, because a disc and a ring, when you draw them, they look very similar. So let's say we have a tiny element here of mass dm. Okay, of course its distance to the center is just r. So let's say capital R. And let's say the length of this tiny element, so this small arc length, let me just try to indicate it that. So let's say that arc length is dl. Hope you can see that, just that small curvature. So if we call lambda, if we denote lambda the length per unit, the mass per unit length, then lambda should be the mass of the ring all over its length or its circumference, which is just 2 pi radius. Okay, and this should also be equal to the mass of the tiny element all over its length, in this case dl. Hope you can see that. Then the moment of inertia of the ring, so let's say I of ring, would be equals to the integral of the moment of inertia of this tiny element. So that's the integral of the mass dm times the distance from the axis of rotation, which is just capital R, and then squared. We integrate over the entire mass of the ring. So we can replace the expression of dm from here. So we can see here that dm is based on 2 pi r times dl. So this expression becomes I ring becomes the integral of r squared times capital M on 2 pi r times dl. Okay. Then we need to integrate this over the entire length of the ring. In this case, the length would go from 0, okay, to the circumference, because if you start here, suppose you start here and you go around, that's just the perimeter of the ring. So that's going to be equal to 2 pi r. Okay. Then we need to integrate this. So I of ring is going to be equal to the integral from 0 to 2 pi r of, so r cancels r, we are just having here, so let's say dl times rm on 2 pi, and that's just going to be 2 pi r. If you integrate dl, you just have l from 0 to 2 pi r, that's just 2 pi r times capital rm on 2 pi. Okay, so 2 pi cancels with 2 pi, and at the end we have I of ring as mr squared. So this is the moment of inertia of a ring about an axis that passes through the center of the ring and that's perpendicular to the plane of the ring, of course. Then if we want to calculate now the moment of inertia about a diameter of the ring, say Ix or Iy, so this is just a diameter like that, and this is another diameter. The two diameters are perpendicular to each other, and the plane of this axis, so the OXY plane, is perpendicular to the axis Z. So we can apply the perpendicular axis theorem, which we saw in the introduction of the video series, perpendicular axis theorem, which tells us that in this case, Iz is just going to be the sum of the moments of inertia, okay, along two perpendicular axes to Z, in this case Ix and Iy. Remember that we can only apply the perpendicular axis theorem if X and Y are perpendicular to each other, okay? So we actually need three sets of perpendicular axes. You need Z, okay, which is perpendicular to other two axes in a given plane, and those two axes themselves must be perpendicular to each other. So take note of that. Due to the symmetry of the ring, Ix would be equal to Iy, okay, because the two are diameters, you can't distinguish between them. So Ix equals Iy, which implies that Iz is going to be 2Ix or 2Iy, as you wish, which implies that Ix would be equals to Iy, which is Iz on 2. And Iz is what we got here. It's just mr squared, so over 2. So Ix equals Iy equals mr squared divided by 2. And that's the moment of inertia of a ring about the diameter of the ring. Okay, hope you understand that. The calculations are really not difficult, just understanding the important theorems, applying them correctly, and doing the integration correctly. You get the result. Okay, see you in the next part of the video series.